All right, in this unit, we're going to be looking at a class of compounds called alkyl halides, or also known as organohalides, as well as the reactions they undergo. This is going to be a very important chapter because organohalides are very common synthetic precursors, which is just a fancy term for saying we use them as building blocks to make much larger compounds. And we're going to get into why that is the case in a little bit. But let's just kind of look at some general properties of organohalides. First of all, what are they? You can recognize them as a compound that contains a carbon-halogen bond. Now, I use the letter X, and that's kind of the convention for a generic halogen, but just to be sure, um, X could be fluorine, chlorine, bromine, or iodine. We're not going to see fluorine a whole lot. It's actually pretty rare, simply just because the carbon-fluorine bond is super strong and not easily broken, which doesn't really make for a very practical reaction. Organohalides can be on sp3 carbons. They could be on sp2 carbons. Just a side note, they call this like a vinyl halide. Vinyl means that the halogen's right on the double bond. If you think of like PVC, PVC stands for polyvinyl chloride. So we'll talk a little bit more about that down the road, but just a little fun fact for the day there. Or the halogen could be on an sp hybridized carbon. And we label them or categorize them kind of similar to how we did with carbocations, where we could have a methyl halide, we could have a primary halide or secondary halide or tertiary halide, depending on how many carbons um, are directly attached to the carbon with the halogen. When it comes to nomenclature, you pretty much know the process of naming them. You just need to kind of know the prefixes we use for them. So fluorine, we use fluoro, chlorine, we use chloro, bromine, we use bromo, and iodine, we use iodo. So, for example, something like this. So here the chlorine is on the third carbon. So we call that 3-chloropentane. Don't forget that if the substituents are on a chiral center, that you do need to name the chiral center. So you can't forget about RNS. Even though we had a test on it, it's going to keep on coming up over and over again. So make sure that you remember how to do those things. So the iodine is on the number 3 carbon, but that is also a chiral center. That's the S stereocenter. So 3S iodohexane. And then it might come up every now and then, but what happens if you got two substituents? One of them a halide, but it's equal distant from another substituent. In this case, the halogen gets the preference in the numbering. So I'm going to number this direction. So here we have 2 fluoro, 4 methyl pentane. Now let's talk a little bit about how we use them, or first of all, why they are useful. As I said earlier, we're going to see these a whole lot in synthesis and making large compounds from small ones. And those smaller building blocks are a lot of times alkyl halides. Um, the reason for that, so why are they so good? The answer is halides are great leaving groups. We talked about this in a previous unit where one of the things that make substances reactive is they can give off something that is a stable ion or stable compound. So If we think about a carbon-chlorine bond, the halides typically are more electronegative than carbon. And so that chlorine's partially negative, which leaves this carbon partially positive. Well, this is a good electrophilic site. And the chlorine, once it leaves, it becomes chloride. Chloride is a very stable ion in solution. And as I said earlier, anything a good leaving group is good because once it leaves, it's stable on its own. Now imagine if we replaced that chlorine, did a substitution, we replaced it with a nucleophile. Now we have something new. We've taken that small building block and we made something larger out of it. This is, as we said earlier, this is a substitution. Or something else that we can do is instead of throwing a nucleophile at it, we can use a base, and instead of doing a substitution, we can eliminate the leaving group. Now, I'll go a little bit deeper into both of these further on down the road in this unit. But it's one thing to know what the good leaving groups are. It's another thing to know why. And I've touched on why, but how can I recognize a leaving group? So a good rule of thumb, the way to recognize a leaving group, the best leaving groups are conjugate bases of strong acids. This is something we've already talked about. Why is an acid stronger than another one? When we talked about acid-base equilibrium, we'd always want to find the stronger acid because the stronger acid would produce the more stable base. So if we think of something like HI, which has a known pKa of -11, that's a pretty strong acid. That dissociates in water to make H plus and I minus. Since HI is so strong, it completely dissociates. It completely dissociates because iodide is a stable ion on its own. So it's a good leaving group. Now let's compare that to another halogen, HF. HF is not a strong acid, so I'll use an equilibrium arrow here, and doesn't completely dissociate. And so, because the F minus ion is not as stable, so it's not a great leaving group. Let's take a look at something else. This is kind of, a little bit of a side trail here, but again, you need to get good at being able to recognize something as a good leaving group or a poor leaving group. Let's compare water to hydroxide as leaving groups. I want you to think of what the conjugate acid of both of these are. The conjugate acid of water is hydronium. What's the conjugate acid of hydroxide? The conjugate acid is water. So let's put this into perspective with, say, a acid-base reaction. So hydronium will dissociate into H plus and H2O. Well, water, we better hope it's stable. It's kind of the important thing that keeps us alive. The conjugate base of hydronium is water, and water is a great leaving group. It's so stable. And we would predict that because the pKa of hydronium is negative 1.7. Now let's compare that. We know water is a good leaving group. What about hydroxide? Well, where does hydroxide come from? Well, that comes from the deprotonation of water. And the pKa of water, if you remember from general chemistry, is 15.7. That's not a strong acid at all. So hydroxide is a poor leaving group.